students, welcome back to the JEE Last Mile Preparation Series 9. Today we will take up questions 17 and 18. But before I do that, by now you already know that I'm Sujata from CBSE NEET JEEchemistry.in, and we are bringing you 2 questions every day until April 4th to help students get that extra edge for their JEE chemistry exam preparation. To keep me motivated in this task, please hit the like button and don't forget to subscribe to my channel. Also, visit my website. The link is in the description below. Let's get started. We continue with physical chemistry. In this session, 2 questions are chosen from chemical thermodynamics. So you have learned 2 parts in that chapter, thermochemistry and thermodynamics, right? So one question is from thermochemistry and the other is from thermodynamics. So here is question number 17. Now this is a numerical value type question found in section B of your exam paper. So let's read this question. There's a lot of data given. We have to write a lot of equations. So we have to be very carefully doing this problem. So from the following data, the N bond enthalpy or bond energy of hydrazine, and look at the physical state. Hydrazine in the gaseous state has to be determined. Okay, you are given the following information. Standard enthalpy or standard enthalpy of formation of hydrazine liquid 50 kilojoules per mole. Standard enthalpy of formation of ammonia gas minus 46 kilojoules per mole. Then average bond energy or bond enthalpy of NH bond, HH bond, and you're also provided with the enthalpy of vaporization of hydrazine liquid. Okay, so let's first write down the equations corresponding to the 2 standard enthalpies of formation. All right, so let's write it here. Let's write down the equation corresponding to the enthalpy of formation of hydrazine liquid. So it involves the formation of 1 mole of hydrazine in its standard state under standard conditions, which is the liquid state, from its constituent elements in their respective physical states at room temperature under standard conditions. And the corresponding enthalpy is 50 kilojoules per mole. So let that be equation number 1. Okay. Now the next information conveyed to us is about the enthalpy of formation of ammonia. So 1 mole. So all enthalpies are with respect to 1 mole. So 1 mole of ammonia is formed from half nitrogen gas and 3/2 hydrogen gas. And the value is minus 46 kilojoules per mole. Let that be equation number 2. Let's focus on these 2 equations. Okay. You have to find out the NN bond energy of hydrazine. Of course, in the gaseous state, but hydrazine. And what are you provided with? NH bond energy and HH bond energy. Okay. In both these equations, you have the HH bond energy. In hydrazine, you have the NN bond and NH bond. And here you have the NH bond. You are not given any information about N triple bond N, which is the bond enthalpy in nitrogen molecule. So we have to get rid of nitrogen. So we have to arrive at a resultant equation which does not have nitrogen. So we have to modify one of the, or maybe both or one of the 2 equations. So let's see which equation we have to modify. We've got 2 equations here. So basically we need to cancel nitrogen. There is 1 nitrogen in equation 1 on the 1 mole of nitrogen in equation 1 on the left hand side. So in order to cancel nitrogen, we need 1 mole of nitrogen on the right hand side in equation 2. So we have to modify equation 2. So what should we do? We want to bring nitrogen to the right hand side. So let's retain equation 1. Okay, we're not making any change to equation 1, which is N2 plus 2H2 giving you N2H4. Let me write down the physical state of hydrazine because you also have N2H4 gas coming up. Okay, now equation 2, we need nitrogen on the right hand side. So we reverse equation 2. We reverse equation 2, but we need 1 mole. We only have half a mole and multiply by 2. So what do we get? We get 2NH3 gas on the left hand side, giving you N2 plus 3H2, right? And here the value was 50. Here the value is, when you reverse the equation, it becomes plus 46, and then you multiply by 2, right? And that is equal to 92. Now let's add these two equations. Let's add these two equations. When we add these two equations, nitrogen gets cancelled out. So what do we have now? 2NH3. Now we have 2H2 here and 3H2 here. So we bring hydrogen to the right hand side. 3 minus 2, 1 hydrogen plus N2H4 liquid. So we added the two equations to get this equation, and therefore we add the enthalpy values, and that becomes 142 kilojoules, right? Now, we need to find out the NN bond energy. We need to find out the NN bond energy of hydrazine in the gaseous state, right? You have been given one information here. Enthalpy of vaporization of N2H4 liquid is 18. So let's write the equation corresponding to that. So N2H4 liquid vaporizes to give you N2H4 gas, and the value is 18. Now let's add these two equations. When you add these two equations, N2H4 liquid gets cancelled. We want NN bond energy in hydrazine gas. So we've got rid of the liquid state. And now what do we have here? 2NH3 giving you hydrogen plus N2H4 in the gaseous state. So all these are in the gaseous state, and this value therefore becomes 160 kilojoules per mole. Okay, so we've arrived at the target equation. Using this equation, we need to find out the NN bond energy in gaseous hydrazine. So it is not an easy numerical. You've got to be very carefully modifying equations and arriving at the appropriate target equation. So let me rewrite the target equation on a separate page. So here we have 2NH3 giving you hydrogen plus N2H4 in the gaseous state. So all these are gases, and the value is 160. So 160 kilojoules per mole is the enthalpy of this reaction. Okay, so now let's write down the various bonds. So since we have to find out the bond energy between of the NN bond, we have to convert all these to the corresponding Lewis structures and identify what are the bonds involved. Okay, so what are the Lewis structures of these compounds? This would be 2 in 2. So I'm writing only the bonds, no lone pairs required. HH plus hydrazine is this. This is hydrazine. Okay, let's write down all the bonds involved here. So here you have 2 in 2. There are 3 NH bonds. Okay, giving you HH plus there is an NN bond whose bond energy we have to find out ultimately plus 4NH. You've got 4 NH bonds on the product side. So you have 6 NH bonds on the reactant side and 4 NH bonds on the product side. So what do we do? 6 minus 4. We have 2 NH giving you HH plus N single bond N. Okay, so the enthalpy of this reaction is equal to the sum of the number of moles of reactants into the total bond energy or enthalpy of the reactants minus summation number of moles of the products, total average bond enthalpy of the products. Right? Now let's substitute. We know that the enthalpy of the reaction is 160. We found out that. Right? Now, what about the bond enthalpy of the reactants? The reactant is this, 2 into the bond energy of the NH bond minus the bond energy of hydrogen, HH bond, plus the bond energy of the unknown NN bond. Now let's substitute the values. This is 160 equal to 2 into. So what is the value given for the NH bond? 393, right? So 2 into 393 minus the bond energy for the HH bond is 436. 436. And the value is 436 plus the bond energy of NN. Okay, so what is this now? 160 is equal to, this is 687 minus 436 minus bond enthalpy of NN. So the bond enthalpy of the NN bond will be equal to 786 minus 160 minus 436, and that is equal to 190 kilojoules per mole. So that will be the answer to the bond enthalpy of the NN bond. All right. So now let's go back to the question. So from the following data, the NN bond energy of hydrazine in the gaseous state is found to be 190 kilojoules per mole. Okay, this is how you solve question number 17. So here is question number 18 from thermodynamics. The value of delta H when 1 mole of a diatomic ideal gas is heated at constant pressure of 1 atmosphere from 27 to 57 degrees Celsius is. So another numerical value type question, which you will find in section B of your exam paper. Okay. The moment you see diatomic ideal gas, you must immediately recollect the ratio of the molar heat capacities at constant pressure to that at constant volume. So for a diatomic gas, Cp by Cv is equal to 1.40. Now, why did we bring in Cp by Cv? Because the delta H at constant pressure is given by the formula Cp dt or Cp delta T. So to find out delta H, we need to find out Cp, the molar heat capacity at constant pressure into the difference in temperature. So we have delta T here. Delta T is equal to 30, right? 30 degrees Celsius. That is the change in temperature. So let's first find out what is Cp. That is why we brought in the ratio of Cp by Cv. You've learned one more formula which has to be used here. Okay, so let's modify this equation in terms of Cp. In other words, 1.40 into Cv is equal to Cp. Right? So we got the value of Cv, right? So now, so what is Cv equal to? Sorry, we've got to get Cv in terms of Cp and then substitute in another very important equation. So Cv is equal to Cp by 1.40. Now, what is the other important equation? The other important equation is Cp minus Cv is equal to R, the universal gas constant. So Cp minus, let's substitute the value of Cv that we got there. Cp by 1.40 is equal to R. So Cp is a common factor. 1 minus 1 by 1.40 is equal to R. Right? So here we get Cp into, let's expand this. 1.40 minus 1 divided by 1.40 is equal to R, right? So what is Cp equal to now? Let's go to the next page. So Cp will be equal to, so Cp is equal to R into 1.40 divided by 1.40 minus 1, which is 0.40. And that is found to be equal to approximately 3.5. So 1.40 by 0.40 is 3.5. So we get Cp as 3.5 R. Now you can directly substitute this information into the formula delta H is equal to Cp delta T. So what is R? And this is in terms of joules. So 3.5 into 8.314 into delta T, which is 30, right? And if you substitute this, if you calculate this, you will get the answer as 873 joules. Okay, so this will be the answer to delta H. If you are asked to find out the value, so you've been asked to find out only delta H in this question, but suppose you are asked to find out delta U, or the change in internal energy, then you must remember the formula CV delta T. So once you get Cp, you can easily get Cv, substitute and get the value of delta U. This is only an additional information. You are asked to find out the value of delta H. So let's go back to the question, and therefore the value of delta H would be approximately 873 joules. So these were two questions from the chapter Thermodynamics, which again involves a lot of numericals, lot of formulae. Okay, so only two concepts have been chosen here. If you have liked today's video, please like the video and don't forget to subscribe to my channel. Also, visit my website. The link is in the description below. See you tomorrow.